Hi guys, Dr. Ricardo. This is the second video in chapter 11 notes, which is on electricity. So we're going to start with one of the most important laws that relate to electricity and physics called Ohm's law. So Ohm's law says that the voltage in a circuit, right? So a circuit is a system that has a load, some kind of power supply, either AC or DC. The load is and the wires in the system are providing the electrical resistance. That's where the energy is going. And the current, which is the amount of electrons that are traveling around in the circuit, right? And what do we know about voltage so far? Voltage is the potential difference across the system. So when you have an electrical system with a large resistance, the large resistance creates a big difference between one side of the resistor and another side of the resistor. So that potential difference, that voltage, is equal to the current times whatever that resistance is. So resistance, again, is the difficulty that you create for the electrons to travel around the circuit. Okay, so it's going to be in a new unit called ohms, O-H-M-S, and it's given the Greek symbol here, which is, I believe, gamma. Okay, so the units are, just like we saw before, voltage is going to be in volts, current is going to be in amps, and resistance is going to be in ohms. So amps times ohms will be equal to volts. Now, underneath that, we could break down both of these units, and we would get a lot of stuff to cancel out, and we would get back to what we know volts are. But I'm going to skip that step. So for you, we can just think volts are equal to amps times ohms. Okay, so let's take a typical easy circuit to look at. This is a toaster in your house, and let's analyze what the voltage, the current, and the resistance is in this particular electric circuit that you set up once you turn the toaster on. So once you push down the knob and you start toasting the bread. Okay, so let me show you that. This is on page 319 in the old book, so I'll show it to you right here. So here's the toaster, right? So we're just going to push down one of these things, right? We're just going to do one at a time, right? And it doesn't matter if I do the left-hand side or the right-hand side, I should get the same number. Most of our toasters are equal. And then this thing over here, right, doesn't have to do with how hot you make it inside the toaster. It has to do with how long you leave the toaster on. So that's actually irrelevant. It's just going to turn on. If you have it on low, it's going to turn off earlier. So you're going to use more electric, but the amount of power that you're going to use is always going to be the same. So we don't have to worry about that. Okay, so figure 10.8 shows a typical household circuit with a toaster plugged in. If the voltage at the plug, the potential difference in the terminals, is 120 volts, okay, so this thing is going to get plugged in. One side of it is is the neutral. The other side is AC at 120 volts higher from peak to peak. So remember, AC goes like this. So where's our 120 volts? Here's 0. It's going to be from the top to the bottom. That's the potential difference at any one cycle. So the voltage is going to be 120 volts peak to peak. Okay, so, and then the second thing is the resistance is given to us, it's 15 ohms. So inside the element that turns electricity into heat are a bunch of different resistors, and they're designed specifically to get hot, right? Because as the electrons flow through them, they're a very tortuous path. They have a very high resistance of 15 ohms. So those toaster elements that are inside here on both sides don't allow the electrons to flow through very easily. The electrons have to force their way through, and when they force their way through, they give off a lot of heat that's radiated out in the form of infrared radiation. The infrared radiation leaves the sides and penetrates into the bread to cook the bread, and that's how we make toast. Okay, so the moment I push this thing down, I connect the circuit. Now, I have, let's say this side is the hot and this side is the neutral. I have this alternating current going back and forth, bouncing back and forth, right? 60 times a second, 120 volts through here, cooks the bread, won't work unless I complete the circuit. I have to allow those electrons to make it back into the system and then all the way back through my house, all the way back to PSE&G because all the wires are connected. So this is plugged right into your wall, okay? All right, so first thing, if we wanted to redraw this electric circuit, we would say, okay, here's my AC power supply. These are my two wires. Doesn't matter which one is the hot one and which one is the dry one. Okay, or which one is the neutral. Okay, and here's my resistor. So I take the toaster element and I replace it with the symbol that you see here. So there's only one resistor in this whole circuit, so we're going to call it R1, and they give us the value of 15 ohms. Okay. The other thing they told us in this circuit is the potential difference across here, right? So this is going to be the hot over here, right? This is the hot wire, and this is the neutral because this is an AC circuit. So I don't have a positive and a negative. I have a hot and a neutral. Okay. Again, this is typically the white wire. This is typically the black wire that comes into your house. Okay. The ground would run parallel to the neutral. And this AC power supply has a potential difference where this side compared to this side is at 120 volts higher than that side. So what is this thing called over here? This is the AC power supply. Power supply, right? Good. All right, so what do we have? We have the voltage is equal to I times R, right? That's always the case. This case, they want to know what the current going through the cycle is, what through the system is, okay? So we can calculate that because the voltage that comes from the line doesn't change and the resistance in the toaster doesn't change. So we get V is equal to IR, and I want to rearrange that for I, right? So I is going to be V over R, right? Divide both sides by R. I is going to be V over R. And then the last step, I is going to be 120 volts divided by 15 ohms. And the current, 120 divided by 15 is going to give you 8. 120 divided by 15 equals exactly 8. So this is an 8 ohm toaster. That gives you the power of the toaster. So a lot of inside your house, you don't describe all the motors and all of the items that you have by their power in watts. You describe them by their amps a lot of times. So the higher the amperage, the stronger the motor is for a drill or a vacuum cleaner or whatever device you have. Because when you plug it into the wall, the voltage doesn't change. The only thing that can change is the current, okay? So that's the first part of this. We figured the current going through this small little circuit is 8 amps. So there's only one pathway through. I have to go through here, got to go through the toaster, and I have to make it around. So everywhere along this path, how much electricity is flowing? Everywhere along the path, there's going to be 8 amps of electricity flowing, okay? And when the electricity flows, it's 8 coulombs per second. That's what 8 amps means. So you could think about it like pumping water around in a circle. It's the flow of electrons, and it's going to go through this way. Out the hot, it's going to push it to the neutral and back out, right? If you unplug, if you cut this wire here, you cut the neutral, circuit would shut off because there would be no way for the electricity to cycle around. You can't have a one-way circuit. You always have to have a pathway for the electricity to come back, okay? If I cut off the hot, right? If I cut off the hot and I touch the neutral to the ground, I shouldn't get any potential difference. If I have the hot on, okay, it's not the hot by itself that's going to electrocute me, is if I touch the hot and then I touch something else, I become the conductor. I become a pathway for the electricity to go to the next thing, and that's how I get electrocuted. I kind of become the resistor, and I cook instead of the toast. Okay? All right, we're going to come back to this because in a little while we'll be able to calculate what the power is to make a piece of toast. So we'll be able to calculate P. Okay, so far we know we've got the voltage, the current, the resistance, and in a little while we're going to add what is the power in an electric circuit. Again, same formulas for AC or DC. I just don't get to draw a positive and a negative. Okay, so that being said, let's take a look at a system where you have an electric circuit, and in this case, you're going to have 3 different loads on your circuit, but they're going to be in series. See how one comes after the other, comes after the other? That's called a series circuit. I have to do this, then I have to make my way through this one, then I have to make my way through this one. Okay, so this is a DC circuit because I have a negative and a positive. And the way we're going to draw batteries in a DC circuit is I'm going to draw batteries like this. It's kind of cool. I make a small little line, then a big line, then a small line, then a big line. The big line is positive and the small line is negative. This is going to be our battery. Every time you want to have a battery. So this is a battery. And for DC, right, is a DC battery, and this is going to be an AC power supply, right, because it's generating an alternating current like that. So that's the difference. One comes in and one goes out. You don't have a positive or a negative. You just have a hot and a neutral. And you don't have to even draw them. Hot, positive and negative. All right, so these 2 systems that I'm showing you right now are going to be for DC, direct current. All right, so you see that? Let's pretend this is the side that generates the electrons, okay? So in a sense, you can think about it in an analogy with water. You can think about water being held uphill that has a high potential. Okay, I open the gate, it flows down. I go through the first rapid, R1. Ooh, I have to make my way through that. Then I go through R2. Then I go through R3. And then I make it back to the bottom at a much lower potential. This could be like a ride at an amusement park. Then I have to crank my way back uphill, put that energy back in to create the potential difference, and then go around again. So in this particular case, if this was a ride at an amusement park and it was a water ride, you'd have to make it through all 3 rapids. All of the water has the same experience. The current through R1 is going to be the same as the current through R2, is going to be the same as through current through R3. Why? Because all the water has to go the same way. That's what happens when you have a series circuit. Okay? In a series circuit, if any one of these items burns out and I have an open circuit, right, where this thing no longer is here and I have a juncture with a space in between it, right, where it's just nothing. Well, guess what? All of the lights will go out. All of the appliances will go out. Your whole house will be out when one thing breaks, because if I break the circuit right here and there's a space, this is called an open circuit, right? Nothing is in between there. How can this connect with this? So anytime I do that, that would be a bad way to wire your house, because one thing breaks, everything breaks. You don't want that to happen. We wire our homes like this. We wire our homes in parallel with one another, so that any one of the electric boxes, if it goes out or one appliance goes out, not necessarily everything else goes out. The only thing that would go out is anything that was on the same circuit breaker as it. So let's take a look in this case. Again, here's a battery. This is the negative terminal, the one with the shorter side. This one is longer, a little hard to see. I gotta make it that much longer so I can extenuate it a little bit. Okay, that's longer compared to that. So the function of the battery is to push these electrons uphill against where they want to go. Okay, they don't want to go back this way, so they have no choice. Well, they can't go back that way, right? So I push them against where they want to go. They're uphill. They come flying out because they want to make their way back around. What's their motivation? They want to make their way back around to the positive. Same thing over here. What's the motivation for the electrons to leave this way? They can't go backwards. I push them uphill. The only way to get back to the place they want to be is through the circuit. I make a pathway that goes through the circuit. Okay, here I go. Come down. Now watch this. I have 100% of the water coming here. Well, now it has a choice. Look at that. I have a T in the pipe. I don't have any T's in the pipe over here. I just have one after another. When I have a T in the pipe, some of the electrons can go this way, some of the electrons can go this way, and some of the electrons can go this way. So if all three of these resistances are the same and they're equally difficult to get downhill, then guess what? A third of it will go this way, a third of it will go this way, and a third of it will go that way. If one of them is much harder, it has a much higher resistance, let's say this one is twice as hard to go through as this one or this one, then the majority of the water are going to take the easy path. Most of it's going to go that way, and only a little bit will go this way, so it doesn't break up evenly. If they're the same, if the value for R1 was 10 ohms, the value for R2 is 10 ohms, and the value of R3 is 10 ohms, I'd break my water flow into 3 separate streams. And then on the other side, look, they reconnect. So I'd get my 1/3, my 1/3, and my 1/3 back. All the water has to make it back into here. So you can make an analogy which watching water flow through a pipe exactly the same as you can having electrons flow through a wire. Okay? Now, if one of these circuit breaks, right, and I had these appliances, and R3 breaks, if R3 breaks, that doesn't affect R1 or R2, because look, the electricity can still flow around this way and this way. In fact, more of the stream is going to go through here and here. Those currents will go up if it can no longer go through here. So if I block this out by taking a pathway out, if there's nothing there, there's no way for the electrons to jump across. Okay, I'm not going to have any sparks. So if I break this Christmas light, the other ones can still work. This would be a bad way to have a string of Christmas lights. If one light breaks, they all break. This would be a good way. This is the way they're wired in parallel. Okay, now, all right, so here, 100%, let's say I had 10 amps of current. The 10 amps would all go through R1, all go through R2, all go through R3. Here, if I had 10 amps and they were equal resistances, 3.3 would go here, 3.33 would go here, 3.33 would go here, and then those currents would get back together again. So that's what happens to the currents. The currents all add up together. The current is the same through a bunch of resistors that are in series. The currents add up to the total current for all the resistors that are in parallel. Okay? All right, so we're going to practice that a lot more, but I want to show you the last important formula. If you want to know what the power is, and we know what power is, it's in the units of watts. It's joules of energy per second. So a joule per second is a watt. Well, electrically, the way you can get power is simply by multiplying the voltage in the circuit times the current. So voltage times current gives you power. So we can always figure out what the power is if we know, like in our toaster, that was 8 amps, this was 120 volts, and this was 8 amps. If we multiply those two things, we'll get the power. How does that work out? It works out because watts is equal to volts times amps, and volts are joules per coulomb, while amps are coulombs per second. So those are the two definitions I originally gave you. So the coulombs cancel out, and I get joules per second, which is the unit of power that we've had throughout the whole semester. Watts of power are joules of energy that are used up per unit time, which is seconds. Okay, so let's go back to our example here of the toaster. So the question is, how much power does the toaster use up? Well, we know our formula for power is just voltage times current. So the power, in this case, we had the circuit going through our house was 120 volts, and the amperage was 8 amps. So 12 times 8 gives me 96. So this is 96 watts. Okay? Okay, well, let's take an estimate for how long of an amount of time it takes to make toast, because we might ask ourselves, well, how much energy does it take to make toast? And then how much do I have to pay PSE&G? So we can go through and do that. And you're going to see you can make toast pretty cheaply, okay? So 96 watts. Well, I'm going to say time to make toast. Well, I think it takes a minute and a half at most to make toast. Maybe 2 minutes you have it in there, and probably the toast will be too brown. So I'm going to say 90 seconds, which is a minute and a half, right? So I could put 1.5 minutes or 90 seconds. I need to get this down to seconds because in order to get energy, right, or work, right, electrical work, energy or work, I need to take the power times the time. So the power was 96 watts multiplied by 90 seconds, and that's going to give me how much electrical energy I used from the circuit. And then we'll see how much we would have to pay for it. Okay, so 90 by 96 gives me 8,640 watts. Okay. All right, and so next thing, we need to change that, right? Oops, sorry. We need to change that watts into kilowatts and then multiply it by hours because that's the very unusual unit of time that, a unit of energy that Con Edison uses, right? So number of kilowatts used. Okay, so how many kilowatts? Now for that very short period of time, right? I'm going to be using a high power, but I don't make toast all day, right? If I made toast all day, I would, like in a restaurant, the toaster would use a lot of energy. The toaster in my house doesn't use much energy because I'm just using it for 90 seconds out of the course of a whole hour, which isn't very much at all. So first I'm going to change this to kilowatts. So in kilowatts, this is going to be 8.64 kilowatts. Why? Because 1,000 watts makes 1 kilowatt, so you have to move the decimal place 3 times. Okay, last, I need to multiply by the amount of time that's in 1 hour in this conversion factor. So 1 hour has how many seconds in it? Okay, 1 hour has 3,660 by 60 seconds, right? Because there's 60 seconds in a minute times there are 60 minutes in 1 hour. So that's where the 3,600 comes from. So this, right, kilowatts is well, I'm going to leave it like that because this is, this is 9,600, this is joules, and this is kilojoules. Okay, so last thing, if I take this and I divide it by 3,600, I'm going to get 8.64 divided by 3,600. .4 times 10 to the minus 3 kilowatt hours. Okay. And if you wanted to see that as a number, I would just need 2 decimal places. Okay. So this is going to be way less than a penny to make a piece of toast. Okay. That's how many kilowatt hours you would use. Again, the toaster uses a lot of energy, but for a very short period of time. Okay. Let me just double check, see if that makes sense. If I go back here, I got my watts. All right, I'm going to try it a different way. I'm going to go back to my watts, which was 8,000. Excuse me. See if I get the same answer. 96 watts of energy, okay, times, oh, interesting. I don't think I needed that last, I think I almost needed to do the seconds twice. If I have this, all I have to do is multiply by how long it's on. So 96 watts, go back to here. This is probably a better way to do it. I don't think this last part came out correct. Okay, so scrap this from here to here. We're going to make toast for 90 seconds. Okay, so this is going to be, I need my toaster on for 120 volts times 8 watts gives me 96 watts. Then all I have to do is multiply by how much 90 seconds is out of an hour, right? So 90 seconds is what fraction of an hour? So 90 seconds times, there is 3,600 seconds in 1 hour. So this is a better way to do it. And then all I have to do is put that fraction of an hour and I'll get watt hours, and then I'll just change it to kilowatt hours. Okay, let's see if I get the same answer. So I get 90 divided by 3,600, 0.025. So 0.025 watt hours, then just change to kilowatt hours. So 96 times 0.025, looks like I'm going to get the same answer, gives me 2.4 watt hours. And if I want kilowatt hours, I have 2.4 watt hours times, in every 1 kilowatt, there are 1,000 watts. So I'm going to get the same answer. So I wasn't wrong here. I just kind of like this way better. Okay, so there goes watts. What's going to be left? Kilowatts times hours. Okay, so 2.4 divided by 1,000. Okay, same answer. Just want to make sure. Times 10 to the minus 3 kilowatt hours. Okay. Each kilowatt, even if I was being very nice to PSE&G and giving them too much money, I'm going to say we pay probably $0.4 per kilowatt hour. Okay, so if I pay 40 cents for each kilowatt hour, and I have 2.4 times 10 to the minus 3 kilowatt hours, right, that's got to go in the denominator. 1 kilowatt hour costs us 40 cents, right? 40 cents is 40 out of 100, so it's $0.4. Okay, so take this times, gotta make toast all day, I had no idea it was so cheap, times 0.4, I get 9.6 times 10 to the minus 4 dollars. Okay, and if I want to get that in cents, I just multiply by 100 times 100. Okay, costs me about 1/10 of a cent, 0.1. Okay, I got 0.096, so 0.1 cents per piece of toast per for each time I make toast. So very cheap. And it's because it's only on for a super short period of time. Okay, so I could make 10 pieces of toast for a penny. All right. So now that we solved that it's not expensive to make toast, let's move on. Okay, take-home lesson. Absolutely have to know Ohm's law. Ohm's law is V times R. Okay. Second take-home lesson. When the resistors are in series, it's very different than when they're in parallel. When they're in parallel, the current gets distributed through and then adds back up to whatever it was before. When they're in series, all of the current, let's say the current was 10 amps of current, all of the current has to go through all three resistors. See, here it gets partitioned. Some goes here, some goes here, and some goes here. You have three different channels, and then it recollects. So 10 goes out, let's say 5 goes here, 2.5 and 2.5, then the 2.5 and 2.5 add back up to 5, then 5 plus 5 comes back to 10. It goes around that way, okay? Good. Okay, last thing that we could do is, now that we have this, we can put our two formulas together. We can put Ohm's law together with the fact that we know that the power in a circuit is the voltage times the current. So what I'm going to do is to figure out what the power is, and based just on the voltage and the resistance, I can get one formula for that, and I can get another formula for power based on the current and the resistance. So I can eliminate V if I didn't have V, or I can eliminate I if I didn't have I. And most of the time you don't have I, right? You don't know how much current is going through the circuit. You do know the resistance of that particular object, and you know the voltage in the circuit. So that's probably the more common case. So what I'm going to do is first take this and plug it just the way you see it in for V, right? So if I plug that in for V, I get a new formula. The power is equal to IR times I. See, if I put that in for I, right, what's in parentheses, substitute it in. So this whole thing substitutes in for this, right? You can put this in parentheses too if you want. So what's in parentheses up here? Substitutes. Okay, so how do I simplify that? Power is equal to I times I is I squared R. So that's the first one. Power is equal to I squared R. Okay, second way I could substitute. Okay, let's solve this one, or rearrange this one for I, right? So if I do that, I is equal to V over R. So all I did was algebra. Now this time, I'm going to substitute in for my power equation, right? I'm going to go back into here, and this time I'm going to substitute in for I. Take that away. If I substitute in for I, I'm going to get, forget this for a second, I'm going to get, come down here, right? Substitute in for I get V times V over R. So V times V over R, and then I could simplify that. What's V times V? V squared over R. So I wind up with three formulas for power. This one that was crossed out, that I'll uncross out, and the third one, the original one. So I'm going to get a new piece of paper and put them all down so you can have them in a nice spot. Okay, hang on one second. Okay, so power is equal to voltage times current. Power is equal to current squared times resistance. Power is equal to voltage squared divided by resistance. Okay, all three different ways to get the power. Okay, this is the one you use if you don't have the voltage. This is the one you use if you don't have the current, and this is the one you use if you don't have the resistance. Okay? Very important. Okay, we're going to talk about this a little bit more, I believe on the next page. Yeah, so electrical resistance in power lines and superconductivity. So electrical resistance going through power lines is about, you lose electricity. You lose about 10% of the electricity. So there is a movement that's trying to make superconducting power lines so that there's no losses when you distribute the power out to the cities from the power plants. Okay? We're not there yet, But other effects of superconductivity do work, and we can talk about them a little bit here. And then in the next chapter, we'll talk about another thing that you can do, which is jack up the voltage to very high voltages when they leave the power plant and transmit the power in high voltage power lines to the cities so that you don't lose 10%. You can lose a lot less than that. Typically, the number that we calculated on the next page is about 3% of the electricity from the power plant is lost just by transmitting it out to the cities and towns that need it. So that's one reason to keep the power plants close by, right? The longer the distance that the wires have to travel, the more losses you're going to have because the wires are longer. Okay, so let's read through these notes first. Wires have resistance, so you lose some power as the current moves through the electric transmission lines. What is superconductivity? It is materials have been developed that carry electricity without any resistance, okay? A resistivity is a term for resistance over a distance. So it basically means the same thing as resistance. The first superconducting material, so if you could make room temperature superconductors, you would definitely, and they could make them inexpensive, you would definitely want to make power lines out of that material because they have no resistance or no resistivity. So this is the resistance per foot of line or per meter of line that you have. So these things would have no losses as the material as you traveled through the wires. Okay, so the first superconducting magnets or superconducting devices were made in 1986 at an IBM lab in Switzerland. So first superconductor was discovered by IBM physicists in Switzerland. You had to go to very low temperatures. They only worked when they were below 35 Kelvin, so they weren't very practical. In 1987, another group invented superconducting materials out of yttrium, barium, copper oxide. Those superconducting materials could go all the way up to 100 Kelvin, so that's much warmer. So you don't have to keep them refrigerated to the ridiculous degree that you have to over here. The idea is we're progressing towards what? We're progressing towards room temperature superconductivity. Okay. Today, ceramic superconductors of copper oxides have been made in the laboratory and work up to 0 degrees Celsius. So that's a far cry. That's 273 Kelvin, long way from 35. So you would just have to keep them a little bit cold, like keep them in your refrigerator or your freezer, okay? That's not impossible to do. So in order to gain the ability to conduct electricity without any losses, you just have to keep them a little bit cold. Again, if this progression was made up to this point, that we're already up to 0, the idea of getting materials that are room temperature, that can make it to 25 degrees Celsius, which is basically what room temperature is very reasonable. So that's a direction that we're heading. Again, you also have to make them practical so they work like wires and they're not super fragile, and you have to make them cheap too. Okay. So this is a graph of the resistance of a superconductor versus temperature. So what happens is that the resistance is plotted here in ohms versus the Kelvin temperature. So these materials change their electronic properties based on how cold they are, okay? So as long as you stay below a certain temperature, they have 0 resistance. And then they shoot straight up and have a typical resistance like regular wires. They're still going to conduct, but they're going to have some losses. And then, just like regular wires, as you heat them up further, their resistance is going to get worse and worse, higher and higher. You're going to have more losses as the temperature goes up. So the idea is, what temperature do you want this to be? 273 is 0 degrees Celsius, right? So we really want to be over here. We want to move this graph so the line doesn't pick up until we get to like 30 degrees Kelvin or even 35 degrees Kelvin, which would be the hottest they would ever be on the warmest day in Arizona. You'd still be superconducting. So that's something that's not unreasonable that can happen, okay, is to have superconducting materials above room temperature. Right now, we're stuck about here, right? We need to get a little bit further so that we wouldn't have to keep them cold. Okay. Here's some applications of superconductivity. Underground high voltage transmission lines, right? So you need to, these things would be kind of expensive to do, so you wouldn't want to string them on wires the way we currently do. They would go underground. The other thing you could do with them is you can make superconducting coils to store electricity, right? Since there's no loss to resistance, the electricity could be held in there until you need it without losing any. Right now, there's not really a way. Batteries don't work that well. There's losses in moving the energy in and out of the batteries. They're currently used, superconducting materials are currently used in medical imaging devices, particularly in MRI devices. MRI devices need a huge magnetic field in order to image what's broken in your body. You need to differentiate between the nuclear spins for healthy tissue versus unhealthy tissue, or a fractured bone versus an unfractured bone, and that's the way the MRI works. So you're actually placed in, when you're inside the MRI, inside a huge magnetic field, and then they probe you with radio waves and see how much of those radio waves and at what frequency are emitted and which ones your body absorbs, and that's how the MRI works. Another cool thing is magnetic levitation. It's called the Meissner effect. Okay, really cool is that when a material is superconducting, it creates such a large magnetic field that it can overcome the forces of gravity, and you can lift something off the ground almost like a hovercraft, and it would just be gliding on its magnetic properties. So it works because the magnetic field induced by the current in the superconductor repels the magnetic field of a regular magnet. So you don't need superconductors on both sides. If you had superconductors either in the train or on the train track, and it just turned on just for that split second when the track comes into contact with the train, then the train will levitate and actually be off the ground and be floating in midair on top of this because of this magnetic repulsion between the track and there's no wheels on the train, right? And the base of the train. Very, very neat. So I'm going to post a video about that. Okay, so they have a lot of these in Japan, especially has maglev trains that go up to 300 miles an hour. Okay, last section that I'm going to do for today is page 9. And page 9 is inspired from a really cool graphic in the new textbook. So I'll grab that. Okay, so when I'm going to show you from the textbook in a second, okay, but when a power plant, any kind of power plant, it could be a coal-fired power plant, a nuclear-fired power plant, gas-fired power plant, the typical voltage of the electricity that leaves the power plant is 20 kilovolts, which is high, but not very high, okay? So unless you have homes that are right in the vicinity of the power plant, within a few miles, then what they usually do is they put it through a transformer, okay? And this is called the step-up transformer, and it raises the voltage and lowers the current so that the voltage that's going through the transmission lines, oh, I'm sorry, I didn't write that on here, is 345 kilovolts. So these guys, I'm going to get a different color so my colors match up. So these guys are at 345 kilovolts, okay? So almost 10 times, actually, take that away, more than 10 times the voltage, okay? About 15 times the voltage. This is going from 20 to 340. So when the voltage goes up, the current goes down proportionally. And the reason that is because V is equal to IR, right? So when one goes up, right, to have the same power, another way to look at it is P is equal to V times I. So for the same power, if this goes up by 10, this goes down by 10, and I keep the same power value. So by doing that, I can transmit the electricity over the lines and have much lower losses, right? The amount of energy that's lost just by taking it from the power plant to your community, okay? This is in the town that you live in, different areas of the town. They probably have maybe 5, 6 of these in a typical Bergen County town. There's a step-down transformer that takes it from 345 kilovolts back down, even below where it started at the power plant, to 4 kilovolts. And that 4 kilovolts goes through another transformer that comes to your street. So the wires that are coming to your street are at 4 kilovolts. So this is the power lines that come into your neighborhood. And let's say you have them on telephone poles if you're in an older neighborhood, like I do, then you're going to see those up there. And then there's small transformers on each block, and you and your neighbors get the power off of those transformers. And what's coming into your house? So here's your house, is 240 volts. Okay? Now, the losses here and the losses here are not critical, okay? Because they're not going through miles and miles of distance. The power plants in Bergen County tend to be in the Meadowlands area, and that is a long way from where I live, and a long way probably from where you live, if you live in Hackensack or Glen Rock, or even further north than that, if you live in Paramus. Whatever town you live in, it might be 10 or 15 miles to the power plant. So we're going to move the electricity from the power plant to your particular neighborhood through these high voltage transmission lines. Now, if you want to calculate how much energy is lost, we already saw that we had a formula that the power is equal to the current squared times the resistance. So this resistance is not the resistance through an appliance. All it is the resistance through the wires. So I'm taking a very small resistance, right, for this wires, but over a huge distance, from all the way from the power plant all the way to Paramus, or all the way to Glen Rock, or all the way to Fairlawn, right? This resistance is going to be a reasonable number. So you take the current squared times the resistance. So the higher the current, the worse the situation is. You can't do anything about the resistance, right? We don't have superconducting wires yet, because if we had superconducting wires, resistance would be 0 and the power loss would be 0. Okay, next thing, why the 2 in the formula? Because not only does the AC electricity has to come to you on the hot line, it's got to go back to the power plant through the neutral line. So there's the in, here's the out. So that's the losses times 2. So we take the formula that we already knew for power. This is the resistance through the wires times the current that goes through the wires times 2. Okay, so you can use that formula if you know the current going through the wires. But a lot of times we don't know the current going through the wires. But what we do know is the amount of power that comes out to the community. So another formula, this is from Ohm's law, power is equal to voltage times current. If I rearrange it for current, current is equal to power divided by voltage. Okay, forget this one, this isn't right. Okay, I'm going to take that off in a second. Okay, let me just cover it up. How's that? Okay, so what am I going to do? In my I, guys, I'm going to plug P over V. Okay, so this is the power that comes from the power plant. So if I said, in order to bring that amount of power that's leaving the power plant, what voltage should I take it at to keep my power losses low? So since the voltage is in the denominator, the higher the voltage, the less this factor that we have to square is going to be. So that's the reason that transmission lines are jacked up to huge voltages, right? 20 times, right? 20 times, or excuse me, yeah, 15 times higher than what they leave the power plant. And from here to here, 100 times more than what comes onto my block. And from here to here, right, more than 1,000 times what comes into my house. And remember, we step this down one more time when it gets to the actual sockets that you use in your house, which are half of this. They're at 110 or 120 to 110. Okay, but everybody's got 220 coming into their house. All right, so if I plug my I is equal to P over V in here, and I square it, that will give me this really nice formula. Okay, so let's take a look at this example, and we'll call it a day with that. Okay, so this is C example of the top of page 298 in the Wolfson book, which is your new book. Okay, so before I show you the example, I want to show you this diagram that I made, only right from the book, because they actually show you what these things look like. Okay, so here's the power plant. Okay, this doesn't matter what kind of power plant it is. Almost all power plants that we see have these really cool cooling towers to cool the hot water, the cooling water off. Okay, doesn't have to be nuclear to have that. So this could be our Bergen County gas-fired power plant that you see right about when you're on Route 80. Okay, by Rochelle, not Rochelle Park, Ridgefield Park. You'll see that power plant. Okay, so leaves at 20 kilovolts, goes through a transformer, gets jacked up to 345, makes it miles all the way to your town. Let's say your town is in Hackensack. So Hackensack then, what this transformer, it's called a substation. This substation brings it from 345, from the high voltage power lines, down to 4 kilovolts. That's what comes onto your block. So what's up on your lines on your block are 4 kilovolts. These transformers, they look like cans that are sitting up there. These transformers take it from 4 kilovolts down to 240. The 240 comes off of there down into your house. So long way from the power plant. Okay, 1, 2, 3 transformers. Here's the first ones. Okay, then they get transported. Here's one of those high voltage power lines that you see leave the power plants. Usually nobody's got their house, directly underneath it. There's a byway there, and you'll just be fields where people walk their dogs and stuff like that. Okay, then it comes, here's the substation in your town, takes it from 345 kilovolts down to 4 kilovolts. And again, this is what it looks like at your telephone pole. The job of your telephone pole is to bring it from 4 kilovolts out there to 240 that's coming into your house. Okay, the power along here, guys, is the lowest ones. The reason why they're the lowest ones is they're the most susceptible to being hit by lightning, and they don't want them to get hit by lightning. So up at the tippy top is just a ground wire. Okay, so that one is just designed there that if lightning does hit the pole, it gets carried directly back down to the ground. So if you look up on the top of a telephone pole, the wire up at the top is just the wire that's grounded. Then there's usually communication, so cable and all that kind of stuff. And then lower than that is usually where the electric is. Okay, so you can see the electric come into your house, right? Most of us have this kind of thing, not underground. If you live in a brand new community or a newer community, you might have the electric be underground wires. Okay, so let's take a look at this problem here. And what it does is it just uses this formula right here. So I'm going to read it to you and we'll go from there. So we're given P is equal to 1,244 megawatts. Okay, so this is the amount of megawatts that are leaving the power plant down here. Okay, he uses a particular power plant. Oh, I'm sorry. That is on the page before. The New Hampshire Seabrook Nuclear Power Plant has 1,244 megawatts of energy that's coming off of it. And it's transmitted, the generator's output is 22 kilovolts, okay? So he's able to calculate over here how much the current is that would be leaving there. But again, you wouldn't want that current to be going through the wires, right? That's way too much. You'd lose The wires would get too hot, lose too much energy, wouldn't make it to the people's houses. So what you need to do is you need to adjust it to 350 megawatts. So if I start plugging into this formula, get a new piece of paper. Okay, if you remember how much the power loss is, it's going to be 2 times whatever the power plant's power is giving off divided by the voltage that it's transmitted squared times the resistance inside the wires. Okay? Okay, so with that being said, I have a 1,244 megawatt resistor. So that's the power that goes in my numerator. Okay, mega, guys, is 1,244 times 10 to the 6th. These have to be in watts. Okay, the resistance here is 1.5 ohms. So the wires are pretty good. Okay. Okay, well, wait a minute. Hold on a second. That would be 1.5 ohms, okay? And then evaluate the expression to get the power loss in the in each of the 2 voltages. So at 115 kilovolts, if I would try to bring the power directly like it was, I need the voltage here. Oh, so I would put that guy down here, okay? And I would get, this would be 115 times 10 to the 3rd volts. And I'd have to square all of that. So the loss, this would be if I tried to bring the power to my house at the voltage that the power plant is producing it. Okay? All right, so that's the first case. The second case is if I step it up, I still have the same numerator, same power, right? But now, trying to bring that power into my house, okay? But now I step it up all the way to 345 kilovolts. So instead of 115 down here, excuse me, this is 115 kilovolts, this is 345, right? So really all I'm doing is doubling it. So 115 kilovolts to 345. It's because of the squaring. So this is 345. Kilo means 10 to the 3rd volts. And again, multiply by 1.5 ohms. Okay? If I do these 2 calculations, right? When you square something, it makes a huge difference. I do these 2 calculations. This one, the first one, loses 350 megawatts of power. That's what the loss comes out. This one, at the higher voltage, loses only, well, it's not only, but it's still a lot, 39 megawatts of power. So almost a tenth less, this one compared to this. Okay, this 350 compared to 1200, this guy comes out to be 28% loss. That's terrible. 28% of the energy from here. This number, the answer here is 28% of this. Okay, excuse me, is 72% of this. Right, this is 72, oh, excuse me, this is 28% of this. That's how much the loss is. So only 72% of the power is getting to the people. Can't have that. Here, when this is 39 compared to 1200, how much is lost compared to the amount that's transmitted? That comes out to 3%. So 10 times less losses. So this is reasonable, right? All of this power leaves the power plant. Only 39 is lost. Right? So that means of the 1244, if I lose 39, I get 1205 times 10 to the 6th watts of power make it to my destination. Okay? So number one reason, why do we transport the power at high voltage? because the losses through the wires would be way too much if we didn't. Okay, so we need to jack up the voltage anytime we're going to jack up the voltage, which also lowers the current anytime we're going to try to transmit powers over long distances through electrical wires. Okay, that's it for this video.